The first problem in chapter 4 and 5 on Newton's laws asks us to find the weight of a gymnast and the weight of any object. In this case, the weight of gymnast is going to be the mass of the gymnast times the acceleration due to gravity. And plugging in the numbers, 50 kilograms is the mass of the gymnast. 9.8 meters per second squared is the acceleration due to gravity. This gives us 490 newtons, and keep in mind that a newton is equivalent in units to a kilogram meter per second squared. So if you see a newton or if you see a kilogram meter per second squared, that means the same thing. For part B, if we look at the gymnast, so this is the gymnast, there's a tension from the rope that is upwards, and then there's the mass of the gymnast, or the weight of the gymnast, I should say, is downward. And since the system is in equilibrium, or there's no movement in the rope while the gymnast is hanging, we can say that the sum of the forces, in this case in the y direction, because we only have movement up and down, the forces are only up and down, is 0, which means that the tension of the rope on the gymnast minus the weight of the gymnast has to equal 0, or that the tension on the rope on the gymnast is equal to the weight of the gymnast, which we already know is 490 newtons. Now, for part C, it says find the tension on the rope, find the tension on the cord. And again, if we look at the rope, there's a tension on it going upwards from the ceiling, that is, and there's a tension on the bottom, which is the gymnast. So if we look at the ceiling, and we assume that the rope is weightless, we have the tension going down, and the tension going up is what's acting. And again, if we consider equilibrium, and we notice that there's only movement in the y direction, forces in the y direction, that gives us that T sub c on r minus T sub g on r equals 0. So T sub c on r equals T sub g on r. But T of g on r is what we just found earlier, which is 490 newtons. This is not a surprise, right? Because these two tensions make what is known as a Newton pair, which is the third law of Newton's laws of motion. So this is an example where you can verify or show the case that Newton's third law does actually happen.